This is going to be chapter 14. We try to give you a couple of this section this week, okay? And just organize it so I can talk about it. So it's going to be 14.1. As we go on, if you have any question, you let me know, because this is going to be important to get a good idea of what's going on. So this is it. This is Monday and 7:10. I got the and chapter 14. So we go with the 14.1. 14.1, we are going to talk about the double integral. Okay, what is going to be double integral? In this case, we are going to consider a function of two variables. Okay, you have to know these names of the integration, because the names are going to be different. So as I talk about it, we are going to take a function of two variables, okay? And as we did with the function, we did with the derivative, we freeze one variable and integrate respect to the other one. Okay, so it's like, you know, we are going to build a machine first, and then we come back and we give you the interpretation of the machine. What is the application? What's going to be, you know, geometry of this subject. But to start with, we prefer to do the machine first. Okay, in your book, they do the geometry first, but we do the machine first. If you freeze one variable and integrate respect to the other one, this type of integration is going to be called repeated integrals or iterated integrals. So the first expression that we have to know is this one. Okay, and later on, we do the same thing for the function of three variables. So what is repeated integrals? Repeated integrals, or the other expression is iterated. Okay, iterated integrals. This is where you fix one variable and integrate respect to the other one. And that's our main tools. Okay, main tool for integrating. That's it. Suppose you have a function. When you define the integral of a function of one variable, you define the function on a closed interval. Now, function of two variables would have two variables. So you need a closed interval for each variable. So you have the variable x and the y, one closed interval for the x, one closed interval for the y. We put them together, the result would be a rectangle. So that's why we are going to start defining the function on a rectangle. So suppose the function, okay, the function f of x comma y, function of two variables, is of course going to be continuous to guarantee that the integral does exist, okay, continuous on the rectangle, the domain. It's a closed interval in one variable, in two-dimensional is going to be rectangle, and when we get to the three-dimensional is going to be a cube. Okay, it's going to be continuous on the rectangle. Rectangle would be denoted by R in this section, okay? And if you see this says, you have two closed interval, this is the A, B cross Cartesian product of the sets. This is the way we write it down. Get used to it. So if you see this notation means X is in this interval, X is going to be between A and B, and your Y is going to be between C and D. So you must know it yourself, or sometimes they give you in set notation, or you may change it to the set notation. So this means the rectangle are going to be a collection of points. You see X and Y, such that the first point is in this interval. They are close. Okay, and Y is going to be in this one. So you have to read it carefully, because these are going to be the limit of integration, okay? So this is the notation of a rectangle that we're going to use. So this is a rectangle because if we get the XY coordinates, so you're going to have one closed interval here. You see you get the A and you get the B. This is one of them for the X, and you get one for the, you see the number is C here, and the number is D here. So the X is going to be between A and the B, and the Y between C and the D. So they are going to be, it's going to be formed, the region would form by just getting these vertical and horizontal line together. Okay. So your points are going to be inside, you see inside this rectangle. So this is going to be the rectangle that we talk about it. Okay. So as soon as you read it, your reading is going to be going to the right, to the left is going to be the X. So X is between A and B. Going up and down would give you the Y. Up and down between. So your Y is going to be between C and D. Okay. This is the interpretation that it is in two-dimensional. Then we go to the three-dimensional. It's going to be a box. Okay. It's going to be a box in three-dimensional. So this is going to be our domain. Any question? Make sure you write the proper, proper notation and get a good idea of what is going on. So this is going to be domain of our function. Now those integral that I talk about it. You freeze one variable and integrate with respect to the other one. The symbols are going to be, you see, when we use this symbol, the symbol of integral from A to B, f of x comma y dx. This is it. You see, this means it's like a partial derivative. You fix the y to be constant. You fix the y to be constant, integrate respect to the x. This is one of them. And we are going to have another one. Another one would be integral from c to d. You see, this is the y. Then you get f of x comma y, but this time dy. So you integrate respect to the y here. So you freeze the x. When you do the integral, the result would be a function of y. You replace the y from c to d. Over here, you integrate respect to the x. Y is a constant. When you are done, your function is going to be, okay, and this is it. When you're done, then your function is going to be a function of y because you replace the x by a and b. Over here, your function is going to be a function of x because you replace the y by c. These are going to be called partial definite integrals. Okay, these are going to be called, like the partial derivative this time, are called partial definite. You know that they are definite integrals because we go from A to B. Definite integrals. Okay. Now, again, we explained that when we do this one, we freeze the x. Okay, so the integral from A to B, f of x comma y dx, okay, is going to be the partial, okay, partial definite. We say the partial definite integral, say with respect, you say with respect to the variable x. It's the way we call it. And if you want to find it, again, you integrate respect the x, replace x by a to b. This function would be a function of y, and we can integrate again. And the result, okay, and the result is going to be a function, okay, it's going to be a function of y. Okay, so this is going to be a function of y, so we can integrate it respect to the y. So it can be, okay, it can be integrated again. It can be integrated this time respect to y with respect to the y. So in this case, we write in this case, we write this one. Look at this. So we already got the integral from a to b f of x comma y dx. Now this is a function of y, so we integrate it again. we integrate this new one from C to D, but this time respect to the Y. Okay. So this would be in short, we write it down as integral from C to D. Okay, integral from A to B, f of x comma y, dx, dy. So when you see it, you know how to operate it. It's like you did with the differentiation. Okay, so this means you have to integrate respect to the x first. You integrate respect to the x, then you replace the x from a to b. So the result would be a function of y. Then you come back and you integrate it respect to the y. So when it's given to you, the order is as is. Question? Similarly, the other way around. Similarly, if you integrate respect to the y first, so integral from c to d, f of x comma y dy. You see, we integrate respect to the y, then you replace the y by c and d. So this is going to be a function of x. So we can integrate it now. Integrate it from a to b, but respect to the x. Okay, so we switch the order. So in short, this would be given as a to b. Okay, a to b, integral from c to d, f of x comma y dy dx. You see, these are two different types of, it's like partial derivatives, remember? The partial derivative second order. And of course, we are going to use that previous theorem that we did before, and we arrive at the fact that they are going to be equal to each other, but we discuss this one later. Okay, any question? So make sure you are able to read because you are going to find it for us. Make sure you read it carefully. For the time being, these are all numbers, so as is, it can be done. You have to get used to it. We are going to do it quite a lot. So we're going to practice first to see how we're going to find it and how we're going to operate. Okay, these are going to be called a repeated integral or iterated integral. It's a machine. Is a machine, everything makes sense because, you just freeze one variable. So your function is continuous. You can use all the methods of U substitution, whatever you know as before, and take the integrals. So your first job, a couple of them would be given, and you're going to find it for us, okay? You're going to do one on the next quiz, one on the next. You do quite a lot because all of them, this is going to be the method that you're going to use, okay? But you're going to ask you one on this quiz test and on the final. Everything we learn here is going to be repeated on the final. So let's get the example to see how we're going to operate. You got to be patient. Some of them are not so nice that you like it, but it can be done. But be, patient. So evaluate each integral. That's the first set that we are going to have. Okay. Let's operate. For example, the first one is, this is it. You get quite a lot in your book and your next assignment. So just getting practice. 1 to 2, 1 plus 8xy. Then this is the dy and dx. That's it. Okay, so you do it as you see it. So this means you have to integrate respect to the y first, then respect to the x. Okay, so you can repeat it if you like, or just do it right away. A solution. I'm not going to repeat this. I usually call them I if you like. Okay, you may think about it. If you write I, we understand. So it's going to be equal to, just explain it. We can do it. So I have to rewrite it to show that I'm going to do the y first. So it's going to be integral from 0 to 3. So I have to do the inside first, 1 to 2, 1 plus 8xy and dy. When you are done, you just integrate respect to the x. Some people, they take this one out, they do it and they come back. You can do it if you like, but I usually stay inside and I do the operations. But just, decide which one do you prefer. We don't mind. But you have to show your work, okay? Because they're all definite integral. By calculator, you can get the numbers right away. And we want to see your work, okay? So this is going to be the one. So I stay as is, integrate respect to the y. So x is a constant. So it's going to be 0 to 3. Okay, integrate respect to the y. Integral of 1 would be y. Okay, plus integrate respect to the y is like 8y. X is fixed. It's going to be 8xy squared divided by 2. Integral of y would be y squared over 2. But remember, you have to find it. You see, when y is between 1 and 2. And this is the way we write it down. Okay, y going from 1 to 2. And when you're done, you come back, integrate respect to the x. Again, you can take it out, do it, and come back. Any question? So integrate respect to the y, the root of integral of 1 is y. Integral of y is squared over 2. Simplify, then substitute. It's going to be 0 to 3. Okay, 0 and 3. So this would be 4. So I'm going to have y plus 4y squared, going y from 1 to 2. And when I'm done, taking the integral respect to the x. Oh, I missed the x here, sorry. It's a 4xy squared. So substitute for, this is 0 to 3. Okay, substitute y equal to 2 first, so that give you 2 plus. Okay, if you replace the y by 2, 2 squared would be 4. 4 times 4, 16. So 16x. Now minus, okay, minus. Replace the y by 1, so that give me 1 plus 4x. Okay, everything dx. So combine the like terms, going to be 0 to 3. Okay, 0 to 3, I have to write this one, 2 plus 16x minus 1 minus 4x and dx. Okay, so I end up with 0 to 3. The numbers give me 1 and 16 and 4. That make it to the 12x dx. Integrate respect to the x, which is going to be x plus 12x squared divided by 2, going from 0 to 3. So that give me x plus 6x squared, okay, from 0 to 3. If you put the 3, that give it 3 plus 6 times 3 squared. If you put the 0, everything would be 0. Okay, so it's going to be equal to the 3. 3 squared would be 9. 9 times 6 would be 54. So the 57, the final answer. Okay, so I, or just the integral, is 57. You don't have to repeat it, but I do it just to give you the final, okay, the final answer, which is 57. This is the way you are going to do it. Any question? So again, you can make this one, okay, depends what you want. If you don't like to keep it all inside, just do one integral first and come back and just repeat it, or just put it inside as is. This is a polynomial type. Okay, I'm going to give you various types that we have so that you get used to know what we are going to be expected in different problems. Okay, just refreshing your memory regarding these integrations. Okay, that's the first one, a kind of a polynomial type. The second one is a rational type. Okay, so there's a number 2. So the number 2 is going to be 0 to 1. Okay, and you have 0 to 1. And the function is x over x y plus 1 all squared. And you have the dy dx. Okay, this is the case that we have. So according to our definition, we have to integrate respect to the y first, then respect to the x. You know that it's a rational function, and since this is, you have a power here, you move it up. If there is no power here, you stay where you are, use the natural log. When there is a power, I move it up to get, to get the integrals. So the solution is going to be, I start with the call it I. So I'm going to move this one up. It's going to be 0 to 1. Okay, and I know that I have to integrate respect to the y first. So I'm going to take this integral 0 to 1, and this is going to be x times xy plus 1 to the negative 2, the dy, and then the dx. Okay, you have to use u substitution for this one. Okay, so you know that if you take this one to be u, you need the u prime for the du. U prime is differentiated respect to the y. The one would be x, so the x is already there, which is going to be your du if you like. So you realize that you're using this formula, u to the negative 2 du. And you know that that will give you u to the negative 1 over negative 1, which is going to be negative 1 over u. This is the way, we do it quickly. You can do it, separately. So it's a u substitution. I take this one to be u. I have to find the du. Du would be x dy, which is the x here. So it's like the u prime. We do this type of short form. So that's a u to the negative 2, really. U to the negative 2 would be u to the negative 1 over negative 1. So that would take us here. Any question? So this is going to be equal to the 0 to 1. So u to the negative 1 over u, this is it. So you are going to have, if you like, u to the negative 1, I write down for you. So it's going to be x plus y plus 1 to the negative 1. Okay, negative 1 divided by negative 1, negative 1, and then it must be evaluated from y equal to the 0 to 1. And when you're done, you come back and integrate respect to the x. Any question? So I integrate x times x plus y to the negative 2. Since the u prime and the du is here, it's like u to the negative 1 only. So I'm going to rewrite it and then substitute. It's going to be 1, 0 to 1. I write this one as a negative 1 over xy plus 1. And then y from 0 to 1. And then when you're done, we have to get the dx. Replace the y by 1. So it's going to be 0 to 1. Okay, if we replace it by 1, so that gives me negative 1 over y plus 1 minus, you replace the y by 0. If you replace y by 0, it gives me negative 1, 0 plus 1. Okay, the dx. I made a mistake here, sorry. I replaced the y by 1, so I end up with the x. So this must be x plus 1. Okay, replace y by 1, so that gives x plus 1. Replace y by 0, that gives 0 plus 1. So I have to integrate the 0 to 1. I rewrite it so I have anything. Negative 1 x plus 1, and that would be a plus 1. A plus 1 dx. Any question? So I'm going to integrate with respect to the x. We are going to call this one u. Okay, u prime is on the top. U prime would be 1. So you have to integrate 1 over u du, which is going to be ln of the absolute value of u. Okay, so this is going to be the negative sign stay. It's going to be negative ln. Okay, ln absolute value of x plus 1 is going to be integral of the first one. Integral of 1 is x. Then you have to evaluate it from 0 to 1. Any question? So I just intentionally give you this one so that you see the role of the natural log. Now replace x by 1, so it's going to be negative ln. You don't need the absolute value because it's going to be 1 plus 1. Okay, and the plus 1. Then minus when you replace the x by 0. Okay, x by 0, that gives a negative ln. Okay, ln of 0 plus 1, which is just ln of 1. Okay, plus 0. And you know that ln of 1 is 0. Ln of 1 is 0, so you end up with a, this is it, you end up with a negative ln2. ln2 plus 1. Okay, you can stop here, or ln2 is 0.69. So you can, if you want, I think it's a 0.60. Just check it, it's going to be 1 minus ln half 2. Okay, it would be fine if you write it down in this form, or you can use your calculator to give us this number. Okay, it's yeah, ln2 is 0.69. It's going to be 1 minus point, if you like, 60, 0.69. Okay, almost going to be 0.3. But we accept this one as well, if you give us the final answer in that format. Okay, so this is a kind of natural log type that you will see it. After a while, you will get used to it. Okay, it takes a little bit time, like the partial derivatives that we did, but be careful and it would be fine. Any question? So that's one format of the natural log. The tricky one for this group are exponentials. So I give you one. There are quite a lot of exponential one, and they are easy to operate, but make sure you remember how you handle these. Okay. So let's check one of the exponential for you. So this is going to be our third example, or the third possibilities. And later on we give you trigonometric one as well. So these type are very popular, 0 to ln2, and you get quite a lot in your book, but when you want to pick the one that corresponds to the one that I did over here. Okay, and the 0 to ln2, 0 to 1, this is it, x, y, e to the y squared x, and the dy dx. This is it. You have the exponential function. So I remind you, in the case of the exponential function, you have these. Okay, integral of e to the u du is going to be just e to the u, okay, plus c. And there is one special that we're going to use to see if you have something like, let's say, e to the ax dx. You know that the exponential function never changes. It's going to be e to the ax, but u prime over here is going to be a. When you differentiated, you multiply by a. When you integrated, you divide by a. So this would be useful to know. Okay, u prime, it's the same thing. That's quick. When it's eventually going to be a constant, it's just like dividing. So we have to integrate respect to the y first. Exponential function got the y, so we have to take care of this one. So it's going to be e to the u, if you like. U is like a y squared because the x is a constant. Du would be 2y. So you have to find that du first and then put them together. Okay, so this is the way we do it, solution. So we say that this integral would be changing to the 0 to ln2. Okay, so you have to take care of this one. 0 to 1, x, y, e to the y squared x dy, and then come back and do the x. So this is going to be your u. You must make sure that your u prime is around, and we do it in the short form, but you can do it if you like. Take it out, and you need to have the u prime, which is a 2yx. Remember, you integrate respect to the y. So you already got the x, y, or the yx. So kind of a 2 is missing. If the number is going to be missing, we can create it right away. Okay, it's a short form that would be very useful. So I need a 2 here. So then this integral would be just exponential function. So the way we do it is, so it's going to be equal to, you need a 2 here. So you divide outside by 2. Okay, it's going to be 0 to ln2. And this is going to be 0 to 1. You can multiply this one by 2. You see? You can do the U substitute, but there are going to be quite a lot of these type of ideas. So you better do it in quick form. You can do this one for the numbers all the time, okay? So the U prime is 2yx. To make it into this form, you need to have the U prime here. So I need a 2. So I divide the outside by 2, multiply by 2. So if I need a 5, 1/5, 5. I need a 7, 1, 7. Okay. So that would be useful. Now we are ready. We change this one into the U, and you have your du if you like. So you integrate in e to the u du, which is e to the u. So this is going to be equal to the 1/2 integral from 0 to ln2. This would be just e to the u, which is e to the y squared x, but y going from 0 to 1. When you are done, we come back and you do the x. Any question? So exponential one is going to be quite a lot. You will see it. Just pay attention. Now you replace the y by 1 and the 0 and continue. So this is going to be 1/2 integral from 0 to ln2. Replace the y by 1. So that gives e to the x minus, replace the y by 0. So that gives e to the, e to the 0. Then you integrate respect to the x. E to the 0 is 1, so that gives 1/2 integral from 0 to ln2. So that gives e to the x minus 1. Minus 1 dx. Any question? That's easy to integrate. So the integral inside, in this section, all through the section, is not going to be complicated. So, there may be a couple of, secant cube that you may have to use integration by parts, or sometimes ln x, but otherwise it's straightforward. Okay, now integrate respect to the x, which is easy. Integral of e to the x is just e to the x. So it's going to be 1/2 times e to the x. Integral of 1 would be x. But your x going from 0 to ln2. Substitute, use your calculator if you need it. It's going to be 1/2. Okay, 1/2. We are going to substitute for ln2 first. So it's going to be e to the ln2 minus ln2 minus, replace the x by 0. So that gives e to the 0 minus 0. Okay, it's going to be 1/2. You know that e to the ln2 would be 2, because they are inverse of each other. Minus ln2, then we can substitute later. And over here, e to the 0 is 1. So that gives you a -1. Okay, that gives you -1. And so 2 minus 1 would be 1. So that gives you 1/2 times 1 minus ln2. You multiply inside, so that gives you 1/2 minus 1/2 ln2. We accept that, if you like to use your calculator and find it in decimal, it's up to you. But if it's not going to be application problem, we accept it. But if it's going to be something about the application problem that the result's going to be important with some specific units, then you have to use your calculator. But we accept this one. 1/2 minus 1/2 of ln2. Any question? So be careful about the exponential one. Make sure you don't miss anything when you do with this type of numbers. We're going to have a couple of more of these, and then we talk about it later. Okay, any question? So this is a machine, iterated integrals. Now, the integral that you see so far, the limit of integrations with numbers. So the domain was just a rectangle. But the way we are going to operate for our function, the region that we integrated, so the region can be a non-rectangular region. Non-rectangular region, the rectangle, it's just so-called, what's that? Rectilinear shape, because all the sides are straight lines. But you may have a curvilinear region. If you have a curvilinear region, means, some of these, like going to the beach. Okay, you go to the beach, you know, the area is not all curvy rectilinear. You may get a curve in some place and some place with the straight lines. And so that's why we have to investigate these integrals on those regions as well. So those regions are going to be, we call it the non-constant, we call them curvilinear regions. So these x and the y can depend on the function of x or function of y. We are going to have two different cases. The cases we are going to refer them as a type 1 and type 2 region in this course through this chapter. So I want to introduce them right at the beginning rather than waiting to get to it. So you know what we are expecting, okay? So we are going to investigate iterated integrals or this machine, but on the region that is going to be a curvilinear one. Okay, so you are not going to have constant all the time. So that's it, iterated integral. This is our second group of the information or integral. Okay, how about integrated, iterated integrals or just repeated integrals? But this time with, we call it with non-constant limit of integration. Okay, limits of integrations. Okay, so it means it's not going to be rectangular. Now, as I talk about it, so there's going to be a curvilinear sides, if you like. Those sides can be happen in two groups. So we call type 1. From now on, type 1 region. Now it's going to be type 1 region. The type 1 region is that your x is constant. You see, look at this xy coordinate that we have. This is it. So your x is going to be constant. So x is going to be between, you see, this is going to be your x. Suppose this is a and the b. So this is going to be a, and this is going to be b. Okay, so x is going to be between two constant numbers. X is going to be between a and the b. So this means you go to the right to the left, you see right to the left here. Now, so that give you to a straight line. Okay, that's going to be to a straight line. But on the other side, y is going to be the other part's going to be curvilinear one. So this means you may be given a curve here. You see, you have a curve here, and you have another curve here. Okay, this is going to be the situation you're going to have. So you get the one function is going to be, we call this one y equal to the g1 of x, if you like. And you have another function here that we call it y equal to the g2 of x. So the region in question is this one. You see, this is going to be your region that you want to define your integral. So as you can see, your x is going to the right to the left. Right to the left, you are going to be between a and the b. But for the y, you have to go up and down. You see, up and down. If you go up and down, your y is going to be between two functions, if you like, two curves. So up and down, so y is going to be between, these are going to be the value for the y that you have, the possibility. So y is going to be greater than g1 of x, and is going to be less than equal to the g2 of x. Okay, so this region is going to be called type 1, and you're going to do quite a lot on these type of regions. Okay, so it's going to be the region that's going to be bounded from right and the left by two vertical line, x equal to the a and the x equal to the b. And from the top and the bottom, okay, it's going to be bounded up, if you like, with the function of g2 of x, and bounded below by the function of g1 of x. So the integral that you're going to see for these type of problems are going to be, you see the outside integral, you integrate with respect to the y first because of these functions. So as soon as this would be given to it, this is going to be the way you are going to design it. So you are going to be asked to find the integral from a to b because of the x is constant. Then the integral from, okay, respect to the y would be integral from g1 of x to the g2 of x, okay? Then you have your function f of x comma y. So you know that you have to integrate respect to the y first, then you integrate respect to the x. And you know what does it mean? This is exactly what we did for the other one. So this basically means we have to integrate, you know that this is going to be, you integrate respect to the y first, okay? In respect to the y, so your y would be, you know, see the value of the y would be function of x. So basically the inside would be a function of x and is, you know, eligible, if you like, to integrate respect to the x, and your x goes from a to b. Okay, so this is a type 1 that we may get for later on. Any question? For the time being, we give you everything. But quickly later on, we are not going to give you the integral to find. We give you this shape, if you like. We give you information for the region, then you decide. You have to know that you have to set up your integral in this format. We call it type 1 format. So the type 1 format is x goes from a to b, and the y goes top to the bottom. Okay? Any question? So that's a type 1 for the time being. So don't be surprised if you, instead of the numbers, you may get a function. Doesn't matter. Okay, you can do it. So it's going to be the type 1. The type 2 is the other way around. So it's going to be a type 2 region. Type 2 region is the one that y is going to be straight. Okay, y is going to be within 2 lines, if you like. And the x is going to be a curvilinear type. Okay, so this is going to be the shape that we are going to have. So in this case, the y go up and down. This is it. So you may pick a number c here. Okay, and another number, let's say d here. Okay, so these are going to be horizontal line. Horizontal line. So as you can see, your y is restricted. Going up and down is a 2 line. It's going to be between c and d. Now x is going to be a kind of a curvilinear format. Okay, so you may get, you may get a curve here, and you may get a curve here. Okay, so this curve is going to be x equal to the something we refer to the h1 of y, and we call this one h2 of y. So the region in question is going to be this one now. You see? So as soon as you see it yourself, you say, oh, how am I going to organize this one? You realize that going up and down, you say up and down, you end up with the up, down, y between c and d. Now for the x, you have to go to the right, to the left. If you go to the right, to the left, you end up with these 2 curves. So your x would be between. Okay, this is going to be the one. So it's like, looking at in this format. So the top one for the x is this one. Okay, so this means your x going from h1 of y to the h2 of y. Okay, so in future, when you see it, when all the information are provided, you realize it's going to be type 2. So the type 2 means you have to integrate respect to the x first. Integrate respect to the x, then you substitute, the result will be a function of y, and then you come back and you take care of the y. So this region, setting up of the integral of this region would be, that's it. So you have to start with the c and the d. CD for the y. Then you have to go from h1 of y to the h2 of y. Your function And you know that you have to go with the dx first, dx, dy. So it's important to know which one goes first. Okay, and interpretation is just the same as we did it. So it's a CD, you have to integrate, okay, respect to the x first, and then come back and continue. That's it. Again, fun part is going to be when the information would be given and you set up and you decide which one is better to do it. Or which one do you have to? Because we can switch it, but we got to be careful when we want to switch. So there are going to be cases that there are some integrals which are impossible to find it as is, and you did have a number of them in calculus 1. But with this switching the region, we can do it. But we need a little bit more information to be able to do those type of things. Yeah, okay, so now we extend our machine so the machine can operate when these are going to be a non-constant. So we have to practice again to get to know it, and then we come back and we put it in the context of a geometry and the application problems, and then you will find out, oh, we already done everything we need. That's why I talk about this one first. I switched the order of your book. So we get to know machine first, then we go back and see, oh, what's going on for this type of integration, how we connect, okay? So get to know them, type 1, type 2, from now on up to the end of the course. So, oh, the region is type 1, type 2, and the way you integrate, you just, just have a look and you find out. Okay, so let's get practice. Again, you're going to given a couple of them to find, to see how you operate with your machine. And then another group would be geometry. Okay, so let's practice again. Example, we repeated whatever we did, but this time the limit of integrations are not going to be numbers. So again, we want to evaluate each integral. Okay, evaluate each integral. Evaluate each integral. Okay, so let's go with the first one. The first one is this one, 0 to 2. Okay, 0 to 2, x squared to x. X squared to x, y squared x, integral of the y dx. You see, that's one. It's a type 1. And for the time being, it's just integrating. So we just know how to do it, how to read it. The reading is you have to do the y first. Okay, then the y is function of x, you substitute the result. Okay, so for the time being, no geometry because everything is nicely given. So I go with the I again. So I remind myself that I have to do this integral first, y squared x dy, then I come back and do dx. With respect to the y, so x is a constant, so integral of y squared is y cubed over 3. Okay, so it's going to be simply 0 to 2 y cubed over y cubed x divided by 3. Then y going from x squared to x. Then when we done the x, there is nothing to simplify, so substitute y equal to the x first. Okay, I rewrite it so know what's going on, 0 to 2. So if I substitute the x for y, so that give me x cubed times x divided by 3 minus, if I substitute for y, that's going to be x squared. So it's going to be x squared to the third power times x divided by 3. Just do it. Make sure you're not going to make any mistake. Any question? So when you're done, and then you are going to get the dx. So it's going to be 0 to 2. Okay, let's make it to the x to the 4th over 3. Here, old and the new exponent, you multiply together, 2 times 3, 6. And there is 1 here, 7. So minus x 7 over 3. Okay, x squared cube would be x 3 times 2, 6. And 6 times x. 6 times x would be x to the 7. Okay, and this is going to be dx. And that's it. Integrated again in respect to the x this time. So this is going to be x to the 4th would be x to the 5th divided by 5. 5 times 3, which is 15, minus x to the 7 and 1, x to the 8th divided by 8. 8 times 3, 24. I'm going from 0 to 2. Any question? So that's going to be the case. Now you substitute x equal to 2. So this is it. It's going to be 2 to the 5th minus 15 minus 2 to the 8 over 24. Everything else would be 0. To simplify, 2 to the 5th would be 32. 32 over 15. Okay, minus 2 to the 8. Okay, 2 to the 4th would be 16. That would be 16 times 16, 250. I think it's a 256 over 24. Okay, common denominator to get the result. Common denominator of the 120. You can use your calculator as well. So 120, that would be 256. And that would be 120. It's going to be 256 times 5. 1,280. And the final answer would be negative 1024 over 120. Okay, you can simplify it. So that will be negative 128 over 15 to the final answer. Again, you can use your calculator if you like. So that gives you the final answer. Again, it's not difficult, but we have to get used to it, to this new type of operation that we do. Okay, we do it one by one to get through this. Any question? Now we haven't done any trigonometric one, so this is the time we are going to use one trigonometric one. Okay, already. So that was the type 1 idea. Again, you don't need the geometry, but I did it so that you know it. Then later on, we're going to use it. So the second one, just a trick, x, sine, cosine type, 0 to pi. Okay, 0 to pi is 0 to cosine y. Okay, cosine y, and this is going to be x sine y, then the dx dy. This is it. This is a type 2. Because x is a function of y, so the x is curvilinear and the y is constant, 0 to pi. Again, you will see in future how we're going to check it. So start integrating with respect to the x, which is going to be easy because integral of x would be x squared over 2 only. Okay, so the solution is going to be, call it I. So this is the way I'm going to operate. I keep the 0 to 2 pi. And then I have to do this one first. Again, you can do it right away. That's going to be x sine of y dx when we're done dy. So I have only x here, so x would be x squared over 2. So it's going to be 0 to pi. Okay, x squared over 2, and that's a sine y. And this is it. So I have to go from x, from 0 to cosine of y. So when we're done, then we integrate respect to the y. Okay, so substitute for x equal cosine of y. So it's going to be 0 to pi So that give you cosine square of y. Then you have the sine of y, then divided by 2. Okay, that's when you put the x equal to the cosine of y, then, and then you put the 0, so that gives you 0. Then you come back and you do the dy. Okay, you can pull out this 1/2 as a constant, and 0 will be over there. So to give 1/2, integral from 0 to pi. So what you have now? You have the cosine square of the y, sine of y, then the dy. You know that again, you have to use u substitution. You have to take the u to be cosine of y to make it into the u squared. And you need the u prime for the du. Derivative of a cosine would be negative sine. You see, remind yourself that if you pick the u to be cosine of y, so the u prime or your du would be negative sine. So you need a negative here if you want to do it in short form. Otherwise, you just go with the u substitution in general. So you can create that negative sign by dividing the outside and the multiplying the inside by negative sign. So it's going to be negative 1/2, 0 to pi. It's the way I do it. Cosine square of the y. So I have a negative sine y dy. Okay, and this is your du. This is du, and this is going to be your u square, if you like. So we're simply integrating a u squared du, which is going to be u cubed over 3. Okay, any question? So it's going to be negative 1/2 as before, but you have the u cubed. So which is going to be cosine cube of y divided by 3, but now going from 0 to pi for the y. Okay, negative 1/2 times a third would be a negative 1/6. Okay, so that gives you a negative cosine cube of y over 6, going from 0 to pi. Substitute. So it's going to be negative cosine cube of pi over 6 minus negative cosine of 0 over 6. Cosine of pi is a negative 1, cosine of 0 is 1. So that gives you negative 1 cubed, okay, over 6 plus, I see this is going to be 1. So it's going to be plus 1/6. Okay, negative 1 cubed would be a negative, negative would be positive. So that gives 1/6 plus 1/6, which is a 2/6, and the 2/6 is 1/3 final answer. So the integral is going to be equal to the 1/3. Okay, so we give you various possibilities really, so that you know how we are going to handle this type of integrations, iterated integrals. Okay, any question? So that's a machine so far. Okay, I can give a break now. We come back and we get back to the, okay, what we start with the aspect for the notion of integrals. Okay, so let's just give you preliminary definitions and we go to the break. So this is why I switched these two sections in your book. So what we start really is, this is just a machine. I did this. So the question is going to be interpretation of the integral. Interpretation of the integral of one variable, you know that it's area under the curve. So how we're going to do it, the interpretation is just the Riemann sum. Remember the area, we're going to partition it. You put those partitions together, and that would give you, okay, eventually that give you the notion of the integral as the area under the curve. So in calculus 1, we define the integral in order to solve the area problem. So what's going to be the interpretation for this one? You see, it's a three-dimensional solid. You see the result because your function, you know that your function z equal to the f of x, y, the graph of this function, you know there's going to be a surface. It's going to be a surface, which is going to be a solid, if you like, a three-dimensional solid, a piece of chocolate, if you like. If you have a piece of chocolate, you know, in three-dimensional one, so what we can do is we can cut it into different slices. If you cut it into different slices, each slice is going to be like a cube. So what we can do is we can find the volume of these cubes, not the area, and you put them together. So the things that you're going to have, you see over here, for example, this dx and the dy, this is in two-dimensional would be the area, okay? But this quantity that you got over here is going to be kind of the height of the piece of chocolate that you're going to have. So when you multiply them together, all together, this is going to be a volume. So we can define the, okay, the double integral as a volume of the three-dimensional solid that would be given to you by the surface equal to the f of x and y. Okay, so let's have a quick break. We come back, we give you this interpretation, and then we connect it to this, the one that we started. Okay, and make it the extension of the, okay, extension of the definite integral from calculus 1. So function of one variable, the integral can be represented as area under the curve, but the function of two variables, the integral can be, you know, interpreted as a volume of the three-dimensional solid. Of course, as you did it for the function of one variable, there are other physical interpretations. Okay, so let's have a kind of, you know, it's 11:53. So we come back at 12:10. I give you that interpretation. We put them together, we are ready. We need to just a definition, okay? To be able to finish. We are not done, you know, to finish this one. Okay, see you then. Okay. So we are going to continue to give you those interpretation of the geometry, if you like, of the double integral. Okay, so that is just a machine. So that will take us into in your book, that take you to the 14.2. Okay, so we continue. So what's going to be geometry of this double integrals? Okay, so we get back to again, this is going to be double integrals. Continue. Or the geometry of the double integrals. So I just remind you what we did in calculus 1, okay, for the geometry of the area problem or the definite integral, and then we do it in this case. Okay, recall that. Let's remind you the expressions. Recall that if y equal to the f of x is a continuous function, must be a positive function because you want to talk about the volume. Area is a non-negative. Okay, it's going to be non-negative continuous function. Okay, continuous function on a closed interval, a comma b. Okay, then the area under the curve, then the area. Okay, the area of the region. You know, the region enclosed by the x-axis, the vertical line, enclosed by the graph, y equal to the f of x. Okay, x-axis, and these vertical lines. Okay, and vertical lines. Vertical lines, x equal to the a, and x equal to the b is going to be given by, okay, another color here. Okay, so it's going to be given by, remember the definition of the definite integral. So the area is going to be equal to the integral from a to b, f of x dx. And this is going to be the limit of, remember, sigma of f of ci delta x, if you like, I from 1 to n goes to infinity. Okay, this is the interpretation of the definite integral or the Riemann integral. Okay, and this is what we have. So that's a curve, y equal to the f of x. And this is, for example, this is the a, and this is going to be the b. Remember the way we do it, we partition it into equal parts or otherwise. So we, slice it into or partition it. And then we are going to cover it from inside or from outside by some rectangles. Okay, so the area of each of these, okay. So if you take one of these out, you see, if you take one of those rectangles out. So if you want to find the area of the rectangle, this portion is going to be your delta x. And this portion over here is going to be just the y coordinate of a point, any point. So we call that point Ci, so f of Ci. So each of these rectangles, the area AI is going to be f of Ci times delta x. then I equal to the 1, 2, 3 up to the end. Depends, how many parts are going to pick. So then your area is going to be approximately the sum of the area of those partitioned rectangles. Since each of them are going to be f of c by delta x, so the area would be estimated by the sigma of f of ci delta, delta x and I from 1 to n. And when f is continuous, you know that this is going to be equal to the integral from a to b f of x dx. That's a Riemann integral. Okay, that is going to be Riemann integral. In calculus, in calculus 1. That's the way we do it. So the way we are going to operate, so this result is going to be, so we solve the area problem with this type of integral. We solve the area problem. It's the way we do it in calculus 1. Now, if you replace this function as a function of two variables, the graph is going to be a surface. The result is going to be three-dimensional solid. Then you can slice that solid into the different rectangles, boxes, if you like, or cubes. And then instead of having the dx, we are going to have a dx and the dy that give you two-dimensional. And it's going to be kind of height if you multiply them together. So the result is going to be a volume. So this is the one that we call it the volume problem. The volume problem can be done by the double integral and in future by the triple integrals. So we do it with the double first. So that's a review of the idea. Now, extension. Extension is called the volume problem. So this is going to be the case. The nice problems are come here. What is the volume problem? The volume problem is exactly you copy what I talk about it. But your copy, let me just bring this application if I can and show you. Maybe we're going to do it. We just do exactly the way we did over here. Let me see if I can. This application is the one that we did the other day, Wolfram. So you have to have the access to it. I just post this one for you. You may be able to get it, but let me bring it and share it. I may lose the camera, but I hope so. Not to lose it. Okay, can you see this one? So this is the one that I have on my computer here. So I'm going to bring the double integral here. Okay, so that would be double integral. Okay. So that would be the interpretation of the. You see, that's exactly what we did with the two-dimensional. Now we have a three-dimensional, and this is going to be the curve. So what we do is we are going to partition it into those different format that I talk about it. You see, these are the one. You see, as you can see, each piece is going to be, you see, look at this one. So we partition it. This is going to be a surface that you partition. So each partition is going to be the box here. You see the boxes here, different angle. You see, you have different curves. So as you can see, your region or your solid would be bounded by the surface. Is going to be the surface over here, and the cross section they're going to consider are going to be that cross section in two-dimensional. In that case, going to be rectangle, if you like. Okay, so the top is going to be these curves that we have. Okay, and the bottom one is going to be, see the x and the y here. This is going to be your x, and this is going to be your y. Okay, then x and the y would be changing between two different numbers, if you like. Then for the z part, you have you have the surface. So it's going to be a solid that will be bounded by the graph, by the surface in three-dimensional. And then if you project it in two-dimensional, that give you the rectangle they're going to have. So what we are going to do to get our double integral, you see this is another format. You see, look at this one. Okay, can move this one probably around so that these are going to be the curve again on the top that we have. Okay, so what we are going to do exactly what I did for the function of two variables. So we can find the volume of each of these, okay, these boxes. So the volume is going to be the cross section, which is going to be the x times y. In this case, going to be delta x delta y. Okay, times the height, or this is going to be the z. So if the z would be f of x, y. So the sigma is going to be the same sigma, but you're going to have a delta xi, delta yi, and you put them together. Eventually, we take the limit, and we arrive at the double integral. Okay, any question? So these are going to be the partitioning. So I'm going to summarize it and get the formula. So eventually, the double integral can be interpreted as the area as the volume of the three-dimensional solid, and your solid would have a formula z equal to the f of x, y, and then you should have the restriction for the x and the y to be able to get it. Okay, so let's stop this one and going back to the notebook. It's very good application if you can have it. Sometimes it's free from the different, colleges. If you search it over there, or some part, it should be this. When I download it, they were all free, but I got it from the university. Okay, so going back, exactly I did as we saw it. So we have a cross section which is going to be a rectangle, and on the top we have the surface. Okay, so the interpretation is going to be, now suppose z is going to be f of x, y. That would be the surface on the top. Okay, is again, it must be a positive one, so non-negative. You know that the range is a number, so we can talk about a positive, negative. So it's a non-negative continuous, okay, non-negative continuous function. Remember, the domain of the function is in two-dimensional, so the domain is a rectangle function on the. Okay, we start with the rectangle, then we can change it to the something else. Okay, this is it, the rectangle R, which is going to be, this is going to be your cross section, AB, okay, cross C and D. So this is what you saw over there. X is going to be between A and the B, Y is going to be C and D. Now the volume. So we have those slices, if you like, those boxes, piece of chocolates, if you like. Now we're going to find the volume of each piece and we put them together. So there you are, the volume of the solid. The volume of the solid enclosed by solid, enclosed by the region again, as you saw it, between the z, the surface z equal to the f of x and the y, which was the top cover, and the cross section, which was the rectangle, and the rectangle Okay, rectangle R is given by, we find the volume of those pieces and we put them together. So it's going to be V equal to the limit of sigma. We put them together and then we make it finer and finer and finer. You know, we increase the number of the partitions as in the case of the one variable. So you're going to have those bits, remember, it's going to be CI, or I just call it XI star, YI star. This is stand for that CI in one dimensional, a function of one variable. Then dx di, going to call it delta II, which is the differential of the area this time. I is equal to the 1 to the n, and then n goes to infinity. Okay, remember each portion was a solid, a box. So the volume of the box is going to be the volume of the cross section. Okay, the area of the cross section times the height. This is the height, and that's going to be the area. Now, if you just take the limit and just when these partitions going to be finer and finer, so this would be denoted by a double integral. So it's going to be double integral. Okay, this is it. A to B f of x comma y dx dy, and this is going to be C to D. Okay, so as you can see, the double integral can be defined by the volume that you have. So the double integral, okay, double integral of f on R, the rectangle, is going to be denoted by, okay, so denoted by, this is the way we write it down. We put the R here, f of x, y, dA. Okay, this is the differential of the area, as you saw it, the area of a cross section, and this is going to be the height. So as soon as you see this notation, you should realize that what you are talking about. Talking about the volume or the double integral, this R is going to be the region for that give you the cross section, that give you the limits of integration for the x and the y. So the double integral is denoted by this notation, and of course it's defined by, and is defined by the one that we talk about it. Okay, so I rewrite it. So this is officially the definition of the double integral. Sigma of f of xi star yi star, differential of the area, I from 1 to n goes to infinity. This is geometrical interpretation of a double integral, just a definition of a double integral. Any question? As of the same as the function of one variable in calculus 1, of course, this is not easy to handle. Okay, we did some easy cases in calculus 1, even for that one. So what we need is to be able to get something that keep us going, to be able to calculate it, if you like. In the case of the function of one variable, remember the way you did it, we just connected to the indefinite integral and the idea of the fundamental of calculus. So what we're going to do over here is we are going to connect this one into the iterated integral. Remember the iterated one, integrating respect to the x or the y first, and then we continue. In order to do it, to get through this one, we have a great theorems. This theorem is called Fubini's theorem. This integral is just very special one. You can extend it. We extend this one to very much more general format, but we are going to use it. So this theorem would make things so easy for us. Okay, any questions? So this is the interpretation, the volume. Now, how are we going to find it? Of course, not by partitioning, but we can use this great theorem. So we use this theorem to do the volume problem. Okay, theorem It depends at what level of mathematics you are. You are going to see you're going to see this type of ideas. You know that the notion of integral, as I told you, if you go on in mathematics, it's all integrals. That would form a part of mathematics. We call it the measure theory. Measure theory is the extension of the notion of the integral that you're going to see. You can define integral, you see, now you define integral on closed interval, and you don't have to. So we extend everything, and measure is a function. It's a function defined on a set function. So the application of measure theory is going to be quite a lot. Okay. I'm a pure mathematician, so I call it measure theory. But measure theory is the way you are going to discover probability. So if you are going to be a statistician, you say, oh, this is the probability theorem. But measure theory would extend everything we talk about. It's very dense course and sometimes hard course. If you want to do any graduate studies in mathematics, you have to take one of these courses, measure theory. And if you want to do anything in advanced physics, you have to know it. So Fubini's theorem would be proof in that concept in a much more general term. But we need just we need a special case. So of course we are not going to prove it in this course. So what is going to be Fubini? That's a name. Okay, you can search on internet, you see quite a lot about it. Fubini's theorem will help us to get through this course and the integrations. Great one. In short, tell you that this idea of the volume problem with double integral is the same as the iterated integral. Done. I've already done the iterated one for you. So we are ready for it. Okay, that's it. If f of x and y is continuous. It's not difficult to prove, but it takes time and not a part of this course. If f of x, y is continuous, if you're going to be math major, you take all of this in a course, we call it mathematical analysis. It's going to be analysis 3. Again, it's a tough course. So if is continuous on the rectangle, which is a comma b cross c comma d. If this is going to be the case, that's it. The double integral is the same as the iterated one. So remember, this notation is double integral. dA. We write the dA, then we decide which one is it. Are we going to do the x first or the y first? Okay, this is the way we do it. So this is going to be equal to the iterated integral from a to b, integral from c to d. This is going to be f of x, y, depends on the region. The way I write it down, dy dx, or you may switch it, depends on the type 1, type 2 region, f of x, y, dA, or r. Yes, you can switch it. You can integrate respect to the x first, a to b, f of x, y, dx, dy. Depends on the problem that you have. In both cases, it can be done. Okay. So from geometry point of view means that's it as we talk about it. So geometrically, this is it, the double integral. It's just the volume. The double integral is 1. F of x, y, dA can be considered. Can be considered. Can be considered as the volume. You must know it as the volume of that three-dimensional solid, of the solid piece of chocolate, whatever. The solid, as you saw it in close by, surface on the top, by the graph of, or the surface, by the graph of z equal to the f of x comma y on the top, and the rectangle down the bottom. And the rectangular. So that is the geometry and the beauty really of the double integral. So they may express the double integral in that format that I did, or they may ask for the volume. So you have to know it. You have to know it yourself, that you just switch it into the iterated integral and you find it. So we have the machine and we have the interpretation to do it. Any question? Now let's do it. There are two groups of problems that we're going to have, okay? The machine is already there. You say, astronaut, it's important to set it up, but otherwise you know how to do it. Okay, the setting up are going to be important. You have two different groups. Okay, the first one is a straightforward one. The other one, you know, you have to be careful when the description of the region would be given rather than the formulas. Okay, but nothing to worry about. So there you are, the first one, or the type 1. Evaluate the double integral. Double integral. The notation that they use, you see, this is, and they put the r here, it's double integral. The function y squared dx and the dA over the rectangle. Over the rectangle, r equal to -3 and 2, the first interval, 0, 1, the other interval. See, that's it. So you must know that this means x is between -3 and 2, and the y is between 0 and 1. Double integral, according to the Frobenius theorem, is equal to the iterated integral. You set up the proper iterated integral, and then you find it. For finding it, we already talked about it. Okay, so this is how you think about it. You say, oh, that's it. So this means x is, so you note that this is x, this is y. -3 less than or equal to the, that's it, x between -3 and 2, and y, that's it. So write the definition. Double integral y squared dx. Oh, I'm sorry, that's x. I made a mistake here. Is y squared x. Y squared x. Okay, y squared x. So it's a y squared x dA over r is equal to double integral. These are all numbers, doesn't matter which one goes first. Okay, doesn't matter, you go with the x, we go with the y, both of them are going to be the same. So the way I do it, I just go with the x first, because the integral is easy. You arrive at the same answer. Okay, I go with the x, then I go with the y. So the function is y squared x. So the way I did it, I go with the x first, then I go with the y. Okay, it doesn't matter, you can switch it for this one. Any question? Now integrate. From now on, you know it. You know that this is going to be you keep the x, then you have to integrate this one first. So that would be y squared x dx. When you're done, dy. You can take this one outside and integrate it, come back. I just stay with as is, x. So I integrate x, which is x squared over 2. So it's going to be 0 to 1. So y squared, x squared over 2. So the x going from -3 to 2. When I'm done, then I take the y. Cannot simplify it, so replace the x by 2 and -3, continue. So it's going to be 0 to 1. I'll replace x by 2, so that give me 2 squared times y squared over 2 minus x by -2. So that give me -3 squared y squared over 2. When I'm done, dy. Okay, 2 squared would be 8 here. Okay, would be 8 over 2. 2 squared would be 4. 4 over 2 would be 2. So that gave me 2y squared minus -3 squared would be 9. So minus 9/2 of the y squared. Okay, this is it, dy. You can integrate or you can simplify it. So, common like terms if you like. So, or just integrate, doesn't matter. 0 to 1. So it's going to be 2 minus, you see it's a 2 minus 9/2, which is going to be 4 minus 9, which is a -5/2. So it's a -5/2 y squared dy. So it's going to be -5/2 integral of the y squared is y cubed over 3 to be evaluated from 0 to 1. If you put 1, okay, if you put 1, so that if you, let's go on, this is going to be -5 y cubed over 6. Okay, if you put 1, so that give you -5/6. Okay, it's going to be -5/6 minus 0, which is -5/6. That's it. So the integral would be -5/6. Okay, so this is it. Y squared x dA is going to be -5/6. Remember, it's just evaluating the integral. They didn't talk about the volume. If it's going to be volume, that function inside is going to be a positive function, and your result will be a positive number. But in this case, it's just finding the integral, and the result of the integral is going to be a number. That can be a positive or a negative. Any question? So this is just reading the information correctly. And we are going to do it for the triple integral later on, okay? Anything we do with the double, we just extend it quickly into the triple. So we'll see one of them on the test. So this is your reading is important to know that this is x and the y. There's going to be another one, we get the triple integral. Okay, that's type 1. Any question? So that is straightforward. Next, I finished reading my first notebooks. Okay, the next one is going to be, it's the same problem, but they are going to put them into the context of the volume. Okay, just get to know these. Are you ready? Volume problem. This is the way I'm going to ask you for the volume. Find the volume. Okay, find the volume. Volume of the solid. Volume of the solid that's bounded above. Remember, bounded above by a surface, bounded below by a rectangle. Find the volume of the solid that's bounded above. Bounded above. In that case, it's by the plane. It's like the one that you saw there. The plane is, this is your surface. Z equal to 4 minus x minus y. This is your function, if you like. Z in this the double integral is going to be the height. And bounded below, of course, by a rectangle. Below by the rectangle. Rectangle R, which is equal to the 0, 1. This is the x, and 0, 2, which is the y. That's it. You see, it's the same problem, but description is given to you for the volume problem. This can be done with the triple integral and the double. In this case, it's a double. So you must know that this is it as we did it. This would be your f of xy. Your x is between 0, 1. Okay, your y is between 0 and 2. So, and the volume is just a double integral. So you must know that the volume is going to be double integral of the function f of xy, differential of the area over the r. So you have to bring the information. The information is that when your function is going to be just the z, the height. So your function is 4 minus x minus y. And the rectangle, you already got the rectangle. You see the rectangle is, it's just for information. So this means that this is x between 0 and 1. And this is y between 0 and 2. Okay, so you must know that the volume can be found by the double integral. Now you set it up and just use the Frobenius theorem to find it. So now we say that the volume is going to be equal to the double integral. Again, doesn't matter which one goes first. Okay, so I do x first at 0 to 1. Okay, again, you get the same solution if you just switch it. Okay, 0 to 1, 0 to 2. And the function is going to be 4 minus x minus y. And the way I write it down, I should do the x first, then the y. So that's going to be a formula. Any question? Okay, so rewrite it, do the x first. You can do it right away, or just remind yourself that I'm going to do the x first, 0 to 1, 4 minus x minus y. I do the dx. When I'm done, I come back and do the y. Carefully differentiate respect to the x. So this is going to be 0 to 2. Respect to the x, the integral of 4 would be 4x. Integral of x would be x squared over 2. Y is a constant, so derivative of y would be yx. Like, you know, when we have a 2, 2x, 5, 5x. Okay, so it's going to be 4x minus y squared over 2 minus yx, and this is x. So when x going from 0 to 1, 0 to 1, and when we're done, then we come back and we integrate it with respect to the y. Substitutes x equal to 1. Put the one that gave 4 minus 1/2 and y, and if you put the 0, all of them would be 0. So it's going to be integral from 0 to 2. You put the 1, 4 minus 1/2 minus y. Okay, everything else is 0. Minus 0, and then the dy. Okay, that's it. And dy. So the 0 would be done. Just rewrite it so we can what's going on. 0 to 2, and we have 4 minus 1/2 would be 3/2. 3.5 is 7/2. So that gives us 7/2 minus y. Then I integrate with respect to the y. I just simplify this. 4 minus 1/2, that gives me 3.5. We can now integrate with respect to the y. So that gives you 7/2 of y minus y squared over 2. It's going to be evaluated from 0 to 2. Okay, substitute. It's going to be 7/2 times y, which is 2, minus 2 squared over 2. And when you put the y equal to 0, that gives you 0. So these two would cancel out. We get the 7. And that's going to be 2 squared, 4. 4 divided by 2, that gives you 2. So the result is 5. So the volume is 5. We don't have any units, of course. You know, if it was a unit, we can write it down. See, that's a typical of the volume problem. Okay, so we nicely solve the problems that we know that we proposed. So when the region, you see the cross section is a rectilinear, it's just a number. It doesn't matter. You can easily switch these x and the y to be able to do it. Any question? So your challenge is going to be when this region is not a rectangular one. Okay, we have lots of fun for that part. So I'm going to give you one. Okay, there are a couple of tricky ones. Then I give you those tomorrow. Just give you time a little bit to settle down with this one. And then we get to the cases that would be good for us to, sometimes this integral would be impossible, then we may have to switch. And that would be another fun part of this, okay? So this section is very dense, okay? And you get quite a lot of, all your problem from your quiz, next quiz would be from this section. Okay, so let's get one to get to know it, to see how we're going to handle those. Okay, any question? Nice, it's all nice because you just extend something, from one variable, it would be nice. So, oh, sorry, I have to bring a new notebook because I'm done with this one. Okay. So that's it. Continue with a new one. You need 2 full notebooks for calculus 3. Okay, that's one. So that's it. These are the type that, that you got to be careful. It's going to be the case, those type 1, type 2 region that we talk about it. These are of these categories. And we practice quite a lot on this. There you are. You see, we spent a little bit more time on the double integral so that when we get to triple one, we already done the job really. Then quickly we can take care of that. So what is this? We want to evaluate this double integral. X, Y, dA over R. Now look at the R. Remember in the previous problem, R was a rectangle. So your region was a rectilinear region. No, not this for this. Over the R, the region R. So look at this. Enclosed by, enclosed between, enclosed between y equal to the 1/2 x, which is going to be a line passing through the origin, and y equal to the radical x, which is going to be a curve. And you have the x equal to 2 and x equal to 4. You see, this is a kind of curvilinear region. Now, you have to have a good idea of the region. Some people memorize it and just write it down and you get the solution. That's fine, but you better look into it because sometimes it would be a little bit more involved. Okay, so the way we're going to do it, we have to graph these regions to see what's going on. Okay, so what I'm going to do is your x is going to be between 2 and 4. Your difficulty is going to be the y that you're going to have over here, okay? So the solution is going to be, I like to have a good idea of my region. So what I do is I know that the x is going to be, okay, x is going to be between 2 and -4, and y is going to be between these two numbers to graph, but I would like you to see it because in some other parts you have to decide which one is going to be the best one. Okay, so I'm going to graph this part is going to be a straight line. So I try use the same numbers, so I give me an idea. So again, these are optional. You can use your calculator to graph it to get the idea, but I just do it. So I go with the 2 and a 4 to see what's going on. So if I put the 2 here, 1/2 times 2 would be, okay, that give you 1. If you put the 4 here, so it's going to be 1/2 times 4, so that give me 2. Okay, so this is going to be roughly what I have for the region. Okay, so 2, 1. This is going to be 2, 1. Okay, and the 4, 3, 4, 4 and 2. So we're going 4 and 2. Okay, so it's going to be the one. You pass it through the origin, and you don't have the tool. You don't need a tool. All of them, all parts. So it's going to be y equal to the 1/2 of x. Okay, this is going to be the y. Any question? Then I have the y equal to the radical x. Again, using calculator, you see all of them right away. And we don't mind when you set up your integral. But I stay with the number that I have. So I have the 2 and the 4, so that give me radical 2. And I put the 4, so that give me 2. So this curve would be, again, that it's going to be passing through the origin, but I wanted at 2 and radical 2, so there's going to be 2. Radical to 1 point something, so it would be somewhere here. Okay, then I have a 4 and 2, so it's going to be 4 and that's going to be 4 and 2 again, same point. Okay, so it's going to be kind of, you see, passing through the origin. So this is going to be the case. But you wanted between 2 and 4, so this is going to be 2, and this is going to be 4. Okay, and the intersection, so this is going to be your graph, your region. See, this is going to be the region that you have. Any question? So it's a kind of a type 1 region, if you like, that we talk about it. The type 1, you see, you go to the right, to the left to find out what is going to be the x. So you go to the right, to the left, x would be 2 and 4. Okay, and to get the y, you go up and down. You see, if you go up and down for the y, see, your value of the y would be up and down, up, down, up, down. Between the line, the curve, the line, the curve. So your y is going to be starting from 1/2 of x, and you end up with the curve, which is the radical x. So this is going to be type 1 region that you're going to have. Any question? So I did this one because things were getting a little bit more complicated later. So you know how we're going to pick those region. Sometimes you switch it. You will see that the next lecture it will be too much for today. Okay, to bring those type of examples. But we are going to investigate it. Sometimes it's not going to be a good one. You may have to change it, or it would be easier for the integral to do it. But you have to have a good idea for the region. Use your calculator and graph it for yourself, or just if you have any doubt about it. So now everything is ready. You may know how to find this integral. Any question? So this would be a type 1. That's why we prepare this type of region. So we say, okay, the double integral, according to the Fubini's theorem, is like the iterated integral. as we did it over here. So we have to do the y first. Okay, y start with the 1/2 of x going to the radical x. And then I do the x, which is going to be 2 and 4. And the function is given to you x, y. So we have to do the y and the x. This is the way you set it up. Any question? You must make sure that you set it up correctly. Okay, as a type 1 or type 2. For this one, you didn't have much to worry about it, but we are going to have some region that's going to be more functions involved, okay, and that would be fun to find it. So that gives you an idea. Now the rest are going to be easy to find because we integrate respect to the y first. That give you only y squared over 2, and then you continue. Okay, any question? So that's it. We know how to integrate. So remind ourselves that we have to do the, okay, we have to do the y first. xy dy, and then come back and do the x. Integrate respect to the y with y squared over 2. So it's going to be 2 to 4. So that would be x, y squared over 2. Then y going from 1/2 x to the radical x. And then when we're done, we come back and we do the dx. Okay. So we continue substituting, if you learn like the 1/2, you can put it out. So it's going to be 1/2, okay, 2 to 4 x y squared. You can do all of them at the same time. 1/2 x radical x and the dx. Okay, substitute for the y, for the radical x, so they get 1/2 integral from 2 to 4. It's going to be x radical x squared. Okay, minus x 1/2 x squared. Then the dx. Radical x squared would be x times x would be x squared. So that gives 1/2 integral from 2 to 4 x squared. And over here, 1/2 x squared is going to be a quarter x squared. So it's going to be minus a quarter, okay, minus a quarter x cubed. Okay, so that's going to be x cubed, the dx. Okay, so integral is going to be just Popper rules. No continuity with respect to the x, so you keep the 1/2 outside, and then we have the following. This is going to be x cubed. Okay, that gives you x cubed over 3 minus, this is going to be x to the 4 divided by 4. That gives you 16. Okay, but it's going from 2 to 4. Okay, you have to substitute, simplify these numbers. So this is it. I put the 1/2 here, put the bracket, I put the 2 first. That's going to be 4 first, the 4 cubed. That's a 4 cubed over 3 minus, okay, 4 to the 4th over 12 over 16 minus, if you put the 2, so that gives you 2 cubed over 3 minus 2 to the 4th over 16. So that gives you the result that you are going to have. Okay, then you have to simplify these to put them together. Okay, so this is going to be equal to the 1/2 inside 4 cubed, 4 times 4, 16, 64. So that gives you 64 over 3. And that gives you 4 to the 4th. You can simplify 2 of them, give you the 16. So it's going to be 4 squared, which is 16. Okay, it's going to be minus 16. Okay, if you like 256 over 32. Okay, it's a 4 to the 4th. 4 squared would be 16. You cancel it out, so that gives you 16 or 16 over 1. And inside is going to be minus 2 cubed would be 8, so that gives me 8 third. then it's going to be plus 2 to the 4 to the 16. 16 over 16 would be 1. Okay, I think that's correct. So this is it. 64 minus 8 divided by 3. So that gives 56 over 3. Okay, and that gives you 15. I think that's correct. It's going to be 1/2. Okay, 56 over 3 and the minus 15. Minus 15, 3 times 15, 45. Okay, 45, 56 minus 45, 11. So it's going to be 1/2 times 11/3. 11/6, the final answer. I think that's fine. Okay, 11/6 should be the final answer of this integral. Okay, so this is your main job, to put this together to get the result. We didn't do anything that we have to change the order of the integral, because these are all nicely continuous functions. So as we did it for the Frobenius theorem, you can change the order of the integrations. But the only difficulty are going to be if you get this curvilinear one. When you change it, then you have to switch these functions at the same time. So for some integral, this changing the order are going to be very important. But we stop here and give you a time for for your test, and this would be enough for the double integral today. Okay, so study this carefully. Okay, carefully. The fun part is going to be when we have to switch the order. We do it tomorrow. And then there are some integrals of the double integrals that's going to be very difficult and almost impossible to find. So what we can do is we can switch it into the polar coordinates. So if you switch into the polar coordinate, everything will be nice and we'll be done. Remember, I saw that in your quiz, some of you used the polar coordinate for the continuity. I didn't accept it as I talked about it before. But for the integrations, I'm going to talk about the polar coordinate, of course, and we are going to use it. And we give you the instruction. You see, on those problems, I know that in some of those problems in your book, they give you the instruction. They ask you, apply the polar coordinate to find the limits. But if we don't ask you to apply the polar coordinate to use the limits, you cannot do it. Be careful. A couple of them are going to be on your tests. So do as I did it on the answer key. Otherwise, you won't get the points. Okay. But for the double integral, of course, we give you the instruction, apply the polar coordinates. And in future, sometimes you yourself find out that the polar coordinate is going to be interesting. We are going to have 3 different coordinates: polar coordinate, cylindrical one, and a spherical one. So we do the polar for the double integral, then we bring it up into the 3-dimensional. It's going to be a cylindrical one and a spherical one. And those are going to be those fun parts of this section. Okay, and that's enough for today. Just study this one and just prepare for your test. Do the test and don't miss the tomorrow one, because tomorrow we are going to change the order. It would be quite interesting problems. If you switch it quickly, you see some integral like e to the integral of e to the negative x squared dx. It's a kind of normal distribution in a statistic, and you won't be able to find it. But with the idea of the changing the order in the double integral, you can do it in a matter of seconds. So don't miss it. We'll talk about it tomorrow. Okay, that's it. Any question? So study this one. Good luck with your test, and we continue and we finish this one. By the end of this week, we talk about this, be done with the double integral. So that would be the one that we talk about in your quiz. Okay, take care. Email me if you need anything. Good luck with your test. Just do it. Okay, bye-bye.